Okay. So look, what I want to do is talk about troughs, which have they kind of rhyme with giraffes, and I don't think they're going to make it.
Well, that was my first word, so it's
you told me that, right?
Yeah, right. It's special.
Okay. So
what happened to aborographs?
Well, they may be better, but this is a shortened version. I think really the expression concept is more the one to capture. I really do think this insight that we had earlier about Zeno and the continuum and consciousness is pretty interesting.
Yeah, and all those new links that Richard sent us.
Yes. Those are very good. Wow. And we need to look at all of those.
By the way, have we contacted him?
I believe we have, but we need to contact him more because he's got a really lot of interesting things to say.
Well, he should at the very least apply for the summer school, right?
Oh, sure. Yeah, right. I mean, no, he should interact with us and we should interact with him because he's got lots of interesting things to say. And, we need to do something about it. But for now, we're going to, he did us a big favor introducing us to the MetaMath people and so on. So, okay, let's look at this. Okay, so I want to understand. Do I need to understand these string diagrams yet? Or is that relevant or is that not relevant yet?
Well, we can understand it if you want.
No, I want to understand. I have a very specific thing right now. I want to understand. Okay, so here, I want to understand how, I want to understand the minimal case of this, basically. So I think I need your substitution. Where is your substitution thing? Okay. Which file is it in?
It's a two-way replace, two-way multi-replace, something like that. It's okay. a no ready function.
Okay.
And by the way, I've made this invertible critical dilemma thing.
Oh. Okay, wait a minute. Two-way multi-replace.
Yeah.
Okay, so should I just evaluate all of this?
Yeah, all the gray boxes.
Okay, so 1 minute. Okay. All right, these are the minimal examples. So let me try to understand as I did before. Okay, let's take one of these. But I think I want to understand these rules on their own, so to speak. So let's say false for this and deduplicate false.
Okay.
Okay, so now what is this doing? This is doing, I don't understand, is this doing a multi-replacement on itself?
Yeah, if it's just one, then it's the only thing that it can do. 1-1 basically means it's acting on itself.
Okay, but so we should be able to take your substitution, your individual thing that just does the substitution lemma.
Yes.
And apply it, and it's a thing that eats two things at a time, right?
Yeah. As well as critical dilemma.
Just like lithophagy, this is duophagy. It eats two things at once. Okay, yeah, sorry, Nick. This is, I don't know whether you have
diphagy
or something. Yeah, diphagy. after the lithophagy for alligators that eat rocks. Okay, where is the substitution lemma?
Yeah.
Is this it? But that
Yes.
says substitution lemmas plural.
You're
Is that
right.
what-
Right. Because lemmas plural, because it tries all the positions where it can apply the rule.
I see. Okay, so let me understand an absolutely minimal version of this. Okay, so if the expression is, if my expression is f of a, like, what happens if I just say f of a, and my rule is what? Something like f of x blank, arrow g of y blank, or g of x blank even. Okay, what does that mean? That means it took f of a and it substituted with f of x, and that was the only thing it could do. Okay,
Yeah.
I'm happy, I understand that. Okay, so now let's say that's g of y there. Okay, I don't understand that. What does that mean?
Well, because patterns are canonicalized, it replaced it with a new pattern. So, but you still can rename it into A.
I see, because it's canonicalized. Okay, so this canonicalizes for the scope of this computation, is what you're saying, right?
Just individual individual results, basically.
Okay, but if I said f of a, f of z or something here, just to check that I understand what's going on. Okay, now I'm officially confused. Why is that a blank the same as that a blank? They seem like they should be new atoms of space.
I mean, individual results are still canonicalized.
I see. Okay, I claim that might not be right. Because that would be like taking a Wolfram model rule.
Yeah, that's right. Whenever they combine, I do like the opposite of canonicalizing, like unifying them, unifying my patterns.
Okay, but the point is that you're imagining that this transformation. See, this is why I'm not convinced, because I think in the original, I don't understand this. This thing here in a token event graph is going to produce two outgoing. Let's do this in a token event graph, okay? So let's see. How do I put that into a token event graph? How do I put this rule? I think I just say token event graph. Then what I say is simply list x blank arrow, I claim.
Values, that's
WW, whatever that means. WW, and that's going to be a list. And actually, I have to prune that a little bit because I want to get only those pieces out, right? So
yeah, values, just values.
Okay. Okay, now I'm going to start this with, let's say, just say this creature here. I think I do it with this, like this. And then I say, comma 2 or something. Wait a minute, why am I getting? Okay, that's what I expect. Okay, so now I want to start this with f of a, f of z. Okay, I claim that's not right. Why is it doing that? So it.
Well, I would claim that it's right, because if one this is to be the same token, because it's for all purposes it's just the same pattern. It means just a variable there. Doesn't matter how you name it.
But you say it's been deduplicated.
What?
Yeah, this is deduplicated. So that we want to switch off deduplication.
But even after that, the result is still going to be the same. Well, actually, yeah. Yeah, you're right.
Okay, that's a nice representation from the token event graph of what's going on. That says the substitution just gets applied to this. Okay, I think I understand here. All right, let's try a more realistic substitution for some actual mathematical thing. So what do we want to do? Semigroups or something? What did you do? What was the simplest one you did here?
Oh, just maybe group actions. That's fine enough.
Let's do semigroups because they're even simpler.
Mm-hmm.
Okay, so let's. What do you have those anyplace here?
Well, you just use axiomatic theory.
I know. I just don't. What's axiomatic theory? TWP.
Yeah.
What does that mean? What is axiomatic?
You convert it into patterns. No, you like provided the theory.
Okay. Okay, beautiful. That's really nice. Okay, all right. So now we are cooking along. We are going to be able to prove theorems about semigroups. Okay, so let's go ahead and just use substitution lemmas. Okay. And in the token event graph, okay, so how do what we want to do in our theory of mathematics, we're going to start with this and we're going to see what we can prove from it, right? Yes. Which I think is what you've done over here. Is that right?
Yeah.
Do we start from this or do we start from a blank? No, I guess we just start from this relation, right? And so what we want to do is we want to say, I just want to understand what it does. Okay, so substitution lemmas of that relation, self-applied. So I don't think we want the braces there. And we don't need the braces there either, so we just do this. Okay, what did that do? Well, that just gave back the same results again, didn't it?
Yeah. Well, it's so it basically put those brackets in the different places.
Did it?
So
yeah.
Those are just trivially equal things.
Okay, these are both trivially equal. All right, so let's try doing this. Let's try running this in a token event graph for a few more steps. If I'm not mistaken, that's what we can do, right? So let's say we do this. And wait a minute, the correct way to do this will be, okay, so this is first reuse a fixed axiom, a fixed proposition.
It's not going to be very exciting because the only place that the substitution lemma can act on is just basically on itself.
Mm-hmm.
On both sides, it can match only these three things and turn brackets around. So it's not going to be like generating anything new at all.
Okay.
I think we already tried it at some point. I have a déjà vu.
Okay. Okay, that's with token
Let's see both.
deduplication. That's with deduplication false. So now let's do token deduplication true. Right, I also have deja vu on this. So this is saying, with that fixed system, we never get anywhere. Okay. And is this equivalent to the system we get if we always allow it to act on the whole vat? So in other words,
The whole vat acting on itself, you mean?
yes, the whole
Well,
vat.
If it's the whole thing acting on itself, then won't it be the same?
I think it will be, yeah. Okay, so how do we give some juice to mathematics here?
But I suppose that means that the vat persists in some
Well,
way.
hold on. Let me just try operating with the vat on the vat. You see what I'm saying? Because this operates on the vat. This is taking a single element on the vat. Okay, so here what we want to do is we want to say WW and WWR or something goes to this and the rule. Okay, and then here for the initial condition, in order to have it actually be applicable, we got to make two copies of the same thing. What the heck? What does it do here? That's it. How can those two both go to that and then have nothing coming out of it? How can that work? Oh, because there's a null list coming out of the substitution lemmas.
All right.
What's that?
Yeah.
Okay, so in fact, what we want to do is we actually want to join the list WW, WWR to those values from substitution lemmas. Oops.
I think I just have an option for that.
What's it called?
Identity.
What is it called?
Identity.
Just the word
And
identity.
substitution. Yeah, true. Goes to true. No, it's for substitution lemmas, so that they also include itself. Yeah, like that.
Okay, this is looking very similar to something we've seen before. Okay, but so let's see what this does. So there's basically four results here. By the way, notice that that is basically the same graph as we had before for that that trivial 1101 type system.
It does look similar. It does bear some resemblance.
Right. So okay. So in this case, you know, pure semigroup theory with pure substitution has only a finite number of can reach only a finite number of results.
Mm-hmm.
Okay, how do we feed it more juice? Do we introduce another relation, like the relation that A equals A? Let's try it.
Yeah.
Let's try that. Okay, so here, instead of this, we're going to have A blank. I'm still suspicious, Nick, about these naming of variables, but anyway, let's look at that. Well, that wasn't very exciting. Oh, that's because it's only acting. That's because, look, it's picking up one of these. How do we allow it to pick up multiple copies of the same thing?
Multiplicity. Try token multiplicity.
In
option.
what? In
the token length graph. No, the Tonk event graph. Maybe automatic.
I think we still have the same.
No, you still have the same two rules as before.
Oh, I know. For this case, I do. I know I do. Okay. So let's go token multiplicity to automatic. For this case here.
Mm-hmm. Well, that certainly makes a difference.
Still doesn't seem to have any extra.
No, so maybe I spoke too soon.
Oh,
I spoke too soon.
It seems like
What's that?
Well, it can't derive anything new, right? That A goes to A.
Yeah, okay, but how do we get it to derive something? Why is this stuck?
Well, why? Well, critical pair lemmas is another thing. If you don't want to introduce any more actions, but because critical pair lemma can like make subterm only one subterm.
Okay. All right. Okay. So then let's okay. So this is now introduce A goes to A as an axiom. Okay. Let's okay. Okay, let's be minimal here. So we're going to go back here, and the critical pair lemmas always require two things, right?
Yeah, it's the same.
Okay, so let's try here critical pair lemma.
Just without identity. Doesn't have that option.
Okay. Like this?
Mm-hmm. Yep.
Should you keep token multiplicity automatic?
I think not. Let's remove token multiplicity for now. Oh boy.
Yeah, that's kind of explosive. Just try one thing.
I think we just crashed.
Wow.
Okay. Math gets big fast. Okay, let's just try one. My God. Okay, so now let's say vertex list of that. Wow. Well, I need to understand critical pair lemmas, so they do a lot.
Yeah, because there's a lot of subterms that you can unify.
Right? Okay, let's draw these as trees. I want to see these trees. Okay, so let's say most of this, and then can we do the thing of just saying blank? Can we do some kind of blank arrow identity? Or is it, no, it's called pattern, right? Pattern arrow, really what it's saying is pattern arrow first.
Yeah. Right, yes. Your screen kind of laggy.
Oh,
So
it should say pattern error lost actually here.
No, it's fine. You just need to take actual pattern, not the,
What? No, but this A blank, full form
yeah,
A blank.
I get it.
Why didn't
You
that
just
work?
but what first? That would just replace first of two
Oh,
arguments, not as a list.
it's just #1. Pattern goes to #1 ampersand.
Yeah, that's a way to do it.
Okay, so now I think we can just say expression tree /@that.
Yeah.
Oh, for God's freaking sake, that is. How do we get those without labels?
Expression to your heads. It's not about it.
No, what's it called? It's some. How do we switch this off?
No idea. 3-element label.
Yeah.
Something with 3-element label. None. Oh gosh. It's not even documented. I have no idea. Can you just make it into a graph?
Yes, but I want to leave it as a tree. I want to leave it as a tree because I think that's.
Well, I mean, preserve the same layout, but make it into a graph.
Yeah, I understand, but I mean, this we just want no freaking labels in the. We should send mail to these guys and ask how to do this, just because.
Yeah.
Let me send mail.
Okay.
Because I remember I've tried to find out how to do it, and also couldn't. So what I did, I just turned it into a graph. Anyway.
Oh, you know what we need to do? This is what we need to do.
Oh, maybe underscore arrow blank.
Yeah, that worked.
Yeah.
Okay, so this is very combinator style. Okay, now I need to understand what a critical pair lemma actually does. Because this is very much like, wow, okay, so let me just understand at a much simpler level. If I just say, okay, so let's say critical pair lemmas of A dot B, oh, I have to do blanks. Wait a minute. What do I do here? I have to have a
2 rules.
What's that?
With blanks. 2 rules. Or 2 rules, doesn't matter.
Okay, so let me just do the most trivial thing.
I had a déjà vu again. It's like,
What's that? Yeah.
déjà vu again.
How do I get the most trivial one of these? What's the most trivial one that works?
Well, this should do something. Oh, you just
What about B goes
go
to A?
change left-hand side into wrap it with F.
Okay.
Into what?
F of A.
Just wrap it with F of A.
On one side or both?
One side.
But is B involved?
It is. It matches.
Okay.
It matches with this A inside F, basically. I'm not sure why it didn't match anything.
I think
above.
you should look at that. I think you should look at this one. That's probably.
Yeah.
Okay, just 1 second. I'll be right back. Just a second.
Yeah, I see that numeraire did not have a
Everything.
Yeah, I know everything. Yeah, right. But
It's just going. It's a discount.
Right,
Have a discount. Oh yeah.
But it's been worse. It's
Sure. It's been worse.
And it's there is something almost equivalent. It appears in late October. So such is the market. Burp. Okay, I'll be right back too.
Hi. Okay. So now, can you explain this to me?
Yeah, and I also can explain why the first case didn't work.
Okay.
It's because I'm not allowed to match against. Well, it's not allowed to match against variables, basically.
Do you think that's right?
Or something like that. Well, I'm gonna look into that, but I do some. It isn't the definition of critical pi-lemma.
Okay. So right means that. Okay. What is the idea here? The idea is, so in a sense, the substitution lemmas. Okay, so let me just. Substitution lemmas are basically like /dot, like replace all. That's basically what they're doing. Correct?
Right.
Okay, what is critical pair lemmas?
So I can only explain it like operationally what it does, not what it is.
Okay.
So what does it do, Nick?
No, by example, like pick the first example first, right? So we have two left-hand sides, f of a and b, right? So it looks for the subterms in the first left-hand side that match against b. That it's not a variable. So A doesn't count, but f of A does, I guess.
Okay.
Oh, it's the other way around.
So
Anyway. So when it finds the subterm, it tries to make unification of variables inside it. Also, like if you add for the critical pair lemma, trace goes to true. It will also add all of those unifications individually. Maybe it would be clear. Maybe it only works for rules. So if you, instead of two rules, just leave it as a rule. It's kind of a new thing.
I think it's more likely that it's because they're not in lists or something.
I'm not sure. I don't know. It's what I did yesterday in order to inverse it from trace.
My God, that's complicated. Does that help you at all? Does that help you at all, that trace?
No, that not really.
Fine.
I need to debug it.
Okay, but fine. Do you think some of these are correct, or do you think nothing here is correct?
Well, they should be all correct because I checked multiple times that at least the output of critical pair lemma does make sense.
Okay, so here, okay, the idea of a critical pair. Gosh, I mean, I thought I've understood this in the case of strings. Let me remind myself what the heck the idea of a critical pair is. I think I've known this like 20 times, and every time I forget what it is. And then I want to understand what the meta idea. Okay. What is the meta idea of all symbolic rules of inference? I think it's basically, is it that variables can be replaced by sub-expressions, by expressions, basically? Is that the basic idea?
Yeah, maybe. Yeah. Right.
So let's see how that relates to the substitution lemma. So the substitution lemma, yeah, what we're saying is, right, variables can be replaced by expressions, then there is a literal, then one uses the rule to say what the transformation is. All right. So in a substitution lemma, which is just like, so the standard Wolfram language story of, you know, f of x blank arrow g of x, for example. If we're presented with f of 7, we first instantiate x blank goes to 7, otherwise known as x. Okay, so in this case, we'll just say x goes to 7.
Mm-hmm.
And then, so this becomes f of 7 goes to g of 7. So here, do this replacement everywhere. Then go from LHS to RHS of the rule. Okay, let's zoom out for 1 second about what that means in mathematics. So the point here is, okay, this is the same thing that we're doing in Wolfram model rules and other things. This is the notion of a pattern, basically. It's just the general notion of a pattern. You know, this do replacement everywhere. Okay, this is the general notion of a pattern, which is what does the matching, together with the general notion of a transformation. Okay, so the confusing thing is, and for strings, for example, okay, for strings, it's confusing. It's confusing because it looks like we're just replacing with literals, but actually, you see what I'm saying?
Mm-hmm.
But in fact, it has to have tentacles saying where it fits in.
Yeah, the unification.
What do you mean?
Well, because if a variable kind of is in multiple places, you have to replace everywhere the same variable.
That's
right?
what we're saying here, yes. I'm still confused by the strings case. Is there a critical pairs story for strings? I think there is, because I think I talked about it in the physics project technical introduction. I'm so embarrassed that I can't remember this. I wrote this way too quickly. It's an absolute devastating sign. Critical pairs. Okay, here we go.
Branch pairs, right?
Yeah. Okay, there's a core set of branch pairs that must resolve. This is about minimal overlapping of strings and so on.
Mm-hmm.
But I'm not sure if this is really, not sure if this is relevant, but that's maybe relevant. Don't know if that's relevant. Okay, so let's come back to your critical pair thing here. Okay, so what you're saying is, my claim is the core idea is variables can be replaced by expressions. Okay, so here, there's a tricky way. Okay, so let's look at the steps here. What does 2 goes to A blank? What does that mean? F of GA goes to F of A.
Mm-hmm.
F. Okay, but so how does it get to that?
Also, so the trace there 2 goes to A blank. It means what was there before, so that I can reverse it there. So it was
Okay.
so A was so before the substitution at position 2 there was A blank.
Okay.
Mm-hmm.
But then it got replaced with GA because it got unified there, right? So when you do it, you basically unify A with G of A, and you replace all A's.
Wait a minute. Why is it with G of A? It's G of B.
Oh, if
So,
actually
okay.
it should be F of B.
Okay, hold on. Let's take this example here. Okay. So the first step is to replace.
The first step is to find the subterm. This is the position one, right? There.
Okay, so that thing there, is that the subterm we're picking? Or it's the
I
A
think so,
blank?
yeah.
Sorry. Nick?
No, this one A inside F.
Yeah.
This
Inside
one
F.
here.
Yeah.
Okay.
That's the subterm.
Okay, so now
Great.
we're going to say A blank goes to. Okay, so one thing we can certainly do is to say A blank goes to B blank. Right, that's a possible substitution. So with that, the first thing becomes F of B blank goes to B blank. So what?
No, you look at the second two rule, right?
Yeah.
So when you found the subterm, finding the subterm meaning that what is matches the left-hand side of there. So F of B blank there matches against this A.
This one here.
Yeah. No.
The
your
subterm. Yeah.
The subterm.
So you take your first subterm, right, and you match it against the left-hand side, the whole left-hand side in the second rule.
Yeah.
Yeah.
Okay,
Right.
so we're saying.
So it's A blank goes to F
okay.
of B blank. Sorry. Okay.
I understand.
It just
Yeah,
makes
right. No, right. I understand that. Okay, so that is just a choice we can make. For fun, we can pick A blank to be F of B blank. Okay. So now if we do that, choose, basically. Choose this. Now, then first transformation becomes.
Yeah. First would be just replace this A with whatever right-hand side was, because
Just-
they're equal.
So
G,
G,
G.
F of B blank.
F of B, what?
G. It is G. So you replace it with the right-hand side because you have this rule.
Yeah.
I
The
see.
second
Choose
rule.
this.
Yeah,
Now use
then you apply that second
rule number
rule.
2
Yeah. Right.
to get A goes to G. F of B is just to G of B. No, G of
Yeah.
yes, G
Yeah.
of B.
B.
Yeah.
It's
Okay.
new
So, okay.
pattern.
So you take the subterm, right? Okay. And then you apply that to the left-hand side of the second rule. And then
Okay,
you basically just apply that second rule. Okay. Yep.
Now what do you do? Now you apply.
Now any other A you replace with the whatever it was if you don't substitute. So F of B.
Right, which is this, which happens here, right? So that means now rule 1 becomes F of B.
F G. You replace that A with G above.
Okay, now use rule 2 to get this.
Just at this particular
Now-
position, you replace this A with G of B.
I see. Now use this.
Mhm.
Why don't I have to apply this globally?
No, that would be just a substitution, I guess, lemma. Or multiple times substitution lemma. Yeah. If
But why does
just-
it work to do this? Why does it work? Why is this something that's mathematically valid?
Well, because these are equalities, right? You obviously can replace just one with the right-hand side, but then you just fix all the other variables with unification in other places. But you actually do substitution at one position.
I am totally confused. Okay, what is the general class of all these possible rules of inference? What is the
I forgot.
general thing you can do? Okay, because in substitution, Okay.
Maybe there's like, if you found a unification procedure, then maybe a general class is just you can apply it only locally. So at all possible positions when it can be applied.
Okay, hold on. In substitution, you're replacing subtrees according to some rule. That's all you're doing. You're replacing matching subtrees according to some rule, right? I understand substitution. Okay, so now what else can you do? And this will work for one-way rules. You can perfectly well do substitution for one-way rules, correct?
Yeah.
Okay, now, when there are two-way rules,
Critical pair also works for rules.
for which? For one-way rules?
For one-way rules.
Of course,
No, it
yeah. We
doesn't.
don't.
Well, look at the physics project
It
example.
does.
Those are one-way rules.
Yes, but that's not. This is not the critical pair lemma that says AB equals ABAA is not true for one-way rules.
Well, right. Okay. It doesn't say they're equal.
No, it doesn't say they're equal. It says
Right.
that this critical pairing, this critical pair lemma thing, say you can say they're equal and they will always converge to the same thing eventually. So I'm saying that's different from saying, if these are two-way rules, this picture immediately implies that ABAA equals AB. You see what I'm saying?
Yeah, I understand.
Yeah.
Right. So when they're two-way rules, if we make, just to make the point with clarity, A goes to B, A goes to C, and this is, let's imagine this is undirected graph. Well, actually, why don't we just put them all in? No, just make it an undirected graph. Oh, for goodness sake. Okay, clearly in that graph, B equals C.
B goes to C.
Yeah, B can be transformed to C
Mhm.
in that graph. But it's not true if this was directed. That's just not true that those things are equivalent. Right, so this is a feature of two-way rules.
We are not saying that they're equivalent. We say we can derive this pair lemma, basically.
What is the pair lemma? Okay, so take this case. This case here. What is the pair lemma? What does that mean? I don't think you're right. I think it only applies.
We just finish like the above example, but we can replace all two-way rules with just one side rule.
Okay, so F of G of B.
Will your code work with one-way rules?
Yeah, it's how it works initially. Just when I provide two-way rules, I just do all combinations of those. That's why I have orientations, so it would be even simple.
Okay, so this one is the same as what we had before.
That's me. I just fixed that above error.
Okay, great. Oops, some debugging stuff got left in. No big deal.
Yeah.
Okay, let me understand this. Why is f of g of a why does f of g of a go to f of a? Because f of anything, f of anything goes to g of anything. So in particular, f of this thing here, f of that a blank.
Yeah, that a blank goes to the g of b, and any other a blank goes to fb.
Right. So okay. So then the direct. So we can now apply. We can say, okay, take. So what's confusing here is the fact that you're canonicalizing the a blanks.
Yeah, that's true.
Okay. So take.
Maybe I should make it an option.
I think you should make it an option. Yeah. Take f of a blank. Okay. Take b goes to b blank goes to f of a blank. Okay. So this is just as a instantiate a variable with b blank goes to f of a blank. Okay. B blank goes to f of a blank. Okay. Now rule 2 is f of a blank goes to g of f of a blank. Okay.
Wait.
Okay, now what? And rule.
Confusing.
I'm totally confused here. And rule 1. I'm totally confused.
What?
Rule 1, according to this, I apply this into rule 1.
In the first position, as before. So.
Okay, so this is in fact wrong. This is in fact wrong. What I'm now doing, instead what I want to do is I say, I'm using the fact that f of b blank, okay, f of b blank matches f of a blank, right? So therefore, we can say
that's the second critical parameter. If you match against this,
is the first one just that f of a blank goes to f of b blank?
No, look, we've got
sorry,
it here.
no. Sorry.
F of g of a goes to f of a.
Yeah, this
so
is
has to happen here.
F of b matches just a,
right.
A, not f of.
Right. Yeah, that's what.
F of b. Okay, so now, okay, f of b matches a blank.
Yeah, because that's the
so
subterm.
Therefore,
yeah.
So therefore, here. Oh God, I don't understand.
Then a blank matches g of b blank.
Then just replace all the a's in the first rule by this f of b, but only except
okay,
the
I see.
subterm.
Now, okay, so now f of b matches a. Now use rule 2 in rule 1. And so that means this becomes, in rule 1, f of b, which is matched to a,
Yeah.
okay, becomes f of b is now g of b. So now that's f of g of b, I want to say, right?
So you want to say A is now G of B.
A goes to G of B. Right. That's what
Okay,
I'm saying.
now use rule 2. F of b matches a.
So look, you have that subterm A in f of a in the first rule. And you just take that subterm and you match it with f of b. So now, okay, so now you've matched it, right? They've kind of traded places. And now you just do what f of b does on any given day, which is it goes to g of b now that they've matched, right? So you have your subterm's now matched.
A matches what? This a is matching what?
So that a subterm in f of a, right? The first thing we do is we match that subterm. Nope, the one on the left. Yeah,
This one here.
yeah, we match that subterm, right? We match that subterm with the left-hand side of the second rule, which is f of b. So that's the first thing that we do. This is the first step. This is what we wrote above.
Okay.
Right. And so now that we're in f of b's shoes, then we just do what f of b does, which is it goes to g of b. You see?
Only for this subterm.
Right.
For every
What is
other
the a? I don't understand. The a allows any b there. What's the b that's there?
It's a new one. Doesn't matter what B. It's just a new variable.
Okay, so then I want to call this, xb. Okay, and f of xb goes to what? Oh, I'm so confused here. I'm really
what
confused.
goes to what? It just
So
you
it's,
have A. Go ahead.
well, just yeah. So
This is why I can't follow these automated proofs.
well, we're in, Stephen. We're delving into the molecular, right? So it's difficult. I mean, so look, you have it written above. We're actually just kind of rewriting it, right? So you have that subterm A on the left-hand side of the first rule.
Okay, can I ask a simpler question? I'm going to ask a simpler question here. Okay, first of all, I really like it if the thing didn't rename things, but let me just try something. Okay, just so I understand this.
Yeah.
Let's say f of f1 of a blank goes to f2 of a blank. Okay, I want to find what is the absolute minimal case. Okay.
Okay. What number is this one? Okay. Yeah.
Oh, that's interesting. Okay, this might help me understand what's going on.
Really?
Okay.
Okay, hold on. What's happening there is that the A blanks. Oh, yeah. No. Why the hell has it gone the other way around? I'm totally confused here. Why has this gone the other way around? I would have expected that F1 of A blank,
Yeah.
the A blank is replaced by F1 of B there. And then the A blank here will be replaced by the F2.
Well, maybe you can do that, but definition of critical parameters at the peak subterm position, you apply the rule, but at another position, you don't.
Okay, so in this case, what we're doing is we're saying this one turns into f of 2 because we applied the rule.
Right.
Right? But then another true statement here should be that f1 of f2 of a blank, this would still be a correct result. Goes to f2 of a blank. That would be a correct result, right?
Yeah, if those were two-way rules, then that would appear among them, among the critical pattern. Because if
Okay,
you
but
swap it,
it's a correct result even with one-way rules. That is a result that imply these two one-way rules together imply this result. Correct?
Yeah, right. But maybe it's not called a critical pattern.
Okay, I don't care. I don't care. I want to understand the general case.
Sure.
Okay, so you're saying, okay, what's the difference between this and a substitution lemma? In a substitution lemma,
well, that would be just a substitution if you leave it like that. You just replace that particular A there using your rule.
Okay, all right.
So it's no different from substitution.
Okay, then what makes it a critical pair lemma?
That replacement also of another A.
But I don't have to do it. This is valid, right?
Yeah, but that's just a simple substitution.
Okay, this is valid, but it's just a substitution lemma.
Yeah.
Okay, but now we sort of double up the substitution lemmas by saying, in addition to that, we're going to replace here. What are we going to do here? We're going to use.
Well, actually, substitution above should be another variable because they should be different. If you apply it.
What should be different? These two variables should be different? No.
It should, because you replaced A with f of B, so this B is new variable. Or f2b.
Okay, so you're saying this should be XA, and that also should be, that's not XA, that's just A, is that right?
Yeah, if you don't touch it at all. So it's just A, but whatever you replace should be a new variable.
Okay, well, there it is, right? You agree that this is correct?
Yeah.
This is valid. Okay, now here, you're saying A, F2 of A. What the hell do we replace F2 of A with? Oh, we replace A.
Yeah.
Oh my God. Okay. Now replace A blank with something from which rule?
The second rule, whatever we matched against with F1 of that new B, the same B.
Now replace A with F1 of B blank. Is that what you're saying?
Yeah.
I don't understand. I mean, that variable can be replaced by anything, right? Why are we choosing to replace it with that? Is that B blank? That B blank can be anything. It's an X B blank again.
No, but first we kind of set on the particular variable when we unified A with F1 of B, right? At this particular subterm. Then we replaced any other A consistent with this replacement.
I am too tired and my head is spinning. Okay. Let's think about where we're going with this. So the basic question is, with these assumptions, wherever they were, where were our assumptions? No, we had assumptions somewhere, which were our fundamental assumptions. Okay, let's just write them down. Oh yeah, here we go.
Here. Right.
So the basic statement of math okay, let's go down here again for a second. Basic concept of axioms slash propositions slash math slash propositions slash math slash rules dot dot dot, whatever you want to call it, is the rules give templates for what should happen that can be applied in many contexts. E.g., string substitution. Wherever ABA occurs, replace it. E.g., cellular automata. Wherever, 101 occurs, replace it. Okay, what's the analog for one of these expressions? Replace this according to the rule. So wherever it occurs, replace it. So in combinators, it's a little bit more complicated because wherever this top of tree occurs, replace it copying the subtrees. You see what I'm saying? That makes sense?
Yes.
Okay, so now what are we doing in our case here? In other words, in that case, we're saying something like K of X blank, S of X blank, Y blank, Z blank goes to X of Y of X of Z or whatever it is. Okay, so we're copying subtrees in that case. Okay, now what happens in these other rules? What happens in these cases? What we're saying is, in a substitution lemma, okay, you copy subtrees. Find where there is a match and copy subtrees. I think it's just like combinators, isn't it?
Yes, kind of. So you just pick a place when you want to substitute. You just copy over.
Right, all the subtrees, but you're copying subtrees. See what I'm saying?
Right, yeah.
Which is a little different from these cases here. In these cases, okay, and then replace it and copy the complement, so to speak. The complementary parts of the string. The unchanged parts of the string. So that's like copying outside of where the change happens, and you're simply copying the outside. Oh, I see. Copy subtrees. Okay, copy subtrees and the supertree. So that's the analog of copying outside here. Right? You're copying the subtrees. What's that?
Supertree is like complementary to whatever branch you've picked.
Exactly. Yeah. Right. It's and the supertree, which is, the supertree is your context, just like the residue in of the unaffected part of a string. Okay. So now right, and that's the same, this is just like combinators. Okay, drum roll. What is the general case? Okay, so I understand copying subtrees. I understand that you match a subtree and you copy it, right? You match a subtree, you copy around its elements. Okay, what is the general case?
So variables, they have this role that they kind of unify different branches of the tree. You kind of postulate that, they were
Okay. Key new idea. X blank and X blank are the same. That doesn't happen in combinators.
Yeah.
Right, that's the idea that goes beyond combinators.
Right. That is an important point. Right.
My God, I am so lucky that I understood so little when I designed SMP. I mean, I sort of understood
you
this
say
stuff,
that so often, too.
Well, it's because I've realized it only in the last few weeks. Because, I mean, all this stuff seemed really obvious at the time. And it is obvious, but as you dive deeper into all this unification and mathematical logic and so on, it becomes much less obvious. I mean, structurally, it's totally obvious what you do with patterns. Okay, so X blank and X blank are the same. So now how does that help you? So what's the minimal case where, so we see f of X blank or something. And how does that, what do we now do with that? That means we get.
When we copy around trees, whether you place X or the whole f of X, you kind of should take care of those.
No, but look, in this case, we're recopying the same tree twice. Right, but we didn't use it in the pattern. In this case,
right,
if we have f of X blank, it's insisting that those two subtrees are the same.
Okay.
Mm-hmm.
Yeah. Right.
It's all going to come down to equivalence classes in the end. It's all going to come down to this, what counts as being the same. I predict what's going to happen is, if we think about this relative to the Rouliad, so to speak, that there is a version of this that is completely unrolled, where all of the stuff is different, and where the things that end up being non-trivial features of this proof graph just never converge, and that they converge when we make certain assumptions about equality. Okay, that's my speculation.
Well, that seems relatively safe. If nothing's ever the same, it's just a free graph. It's just unwieldy.
Yeah. Okay. Hold on. Okay. Let's just understand how critical pairs. So substitution lemmas don't make use of this fact. Is that true? And a substitution lemma, but you have a substitution lemma that says f of X blank goes to something or other. Is that a valid substitution lemma?
Well, yeah. If it's going to match, it's just like a replaceable. If it's going to match against some subterm where there is actually X is the same, they have a same subtree, then it's gonna fire and replace.
Okay, but okay, fine. But is there a version of this that is more general than that? What can you do that is more general than just structurally looking, is the pattern matching? It's something to do with a subterm matching thing. Is that right? I unfortunately need to go to sleep. You guys can continue. You're very welcome to continue. You want to?
All right. I also have a meeting in 5 minutes.
Oh, well, then that's
solutions meeting. Yeah.
Wow, with Europeans probably.
Sure.
Italy
and Australians.
Oh, and
Australians. Oh my God, the world's a crazy place. Okay, well, we should wrap up here, but we clearly, this is the next step, is to try and figure this out.
Well, finally, we're going to actually address this question of variables and what's the same. And I mean, we've danced around this issue, but this is what we have to. This is the core issue of getting. Right. This is what we're basically learning here, is that in the model of that mathematics is more general than combinators in some sense, that there's something additional being done and possibly more general than pattern matching. I mean, it's what we're also learning, is that this critical pair thing, which is probably related to this unification thing, is an additional kind of thing that we might do in the language that is not just pattern replacement. But is this coarse graining that some mathematical observer does?
Possibly, yes. But I think first we have to understand what it is. All right, time to go. Thanks, guys. Sorry, this is a cliffhanger. Well, James, keep thinking about this. You could probably figure this out. I mean, okay, cliffhanger. Nick has to go. I have to go. To be continued as soon as we can.
Okay.
Okay.
Cliffhanger. Yeah. Okay, see you later.
Okay, cheerio.
Bye.
Take care.